Go outside tonight and try to find the nearest star to the sun. If you live anywhere north of Cairo, you can stop. It never rises where you are. Get far enough south and you will find the pointers, two of the brightest stars in the sky. One of them is Alpha Centauri. And neither star you can see there is the nearest star. That one sits 2 degrees off, at 11th magnitude, 100 times too faint for any human eye, which means that in 300,000 years of our species looking up, nobody has ever seen it. Not once. And that is only the first thing wrong with the number everybody quotes. 4.37 light years is not one distance. It is not a fixed distance. Our finest instrument cannot measure it. By the end of tonight, you will know exactly why the distance to Alpha Centauri is far worse than you think. And I promise you now, the reason is not speed, and it is not fuel. Get comfortable. If you are the kind of person who enjoys watching a familiar number quietly fall apart, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, 4.37 light years will not mean what it meant this morning. Now let's slowly settle in. There is a number you have almost certainly heard, and you have probably never had a reason to doubt it. The nearest star system to our own is 4.37 light years away. That number appears in textbooks and documentaries and museum placards, and it always arrives with the same quiet confidence, as though it were a fact of the same kind as the boiling point of water. It is the friendliest figure in all of interstellar astronomy. It is small enough to hold in your head. It is a single digit followed by 2 decimal places, and by the end of tonight, I would like you to understand that it is the least honest number in the entire subject. Let me start by being generous to it. Let me lay it out properly, in every unit a person can actually feel, so that when we start taking it apart, you know exactly what is being taken apart. 1 light year is the distance light travels in 1 year, moving at 299,792.458 kilometers every second. That works out to about 9.46 trillion kilometers, or about 5.88 trillion miles. It is 63,241 astronomical units, where 1 astronomical unit is the distance from the Earth to the Sun, and it is 365.25 light days, which is a unit I want you to hold on to because we are going to come back to it in a way you will not enjoy. The nearest star, Proxima Centauri, sits at 4.2465 of those light years. In kilometers, that is about 40.16 trillion. Written out, that is a 4 followed by a 0 followed by 12 more digits. In miles, it is about 25 trillion. In astronomical units, it is 268,000, which means that if you took the entire distance from the Earth to the Sun, the distance sunlight covers in 8 minutes and 20 seconds, and you laid it end to end, you would need to do that 268,000 times to reach the nearest star. Here is that same distance in human motion. If you started walking at a steady 5 kilometers an hour, and you did not stop to sleep, or eat, or slow down, or die, you would arrive in about 917 million years. That is not a figure of speech. 917 million years ago, the most complex life on Earth was single-celled. The continents were arranged into a configuration nobody has a name you would recognize for. If you had set out then, on foot, without pausing, you would be arriving at Proxima Centauri roughly now. Put yourself in an airliner instead. At 900 kilometers an hour, the cruising speed of a long-haul jet, the trip takes about 5.1 million years. Our species, in anything resembling its current form, is around 300,000 years old. You would need to have boarded that flight 17 times earlier than the existence of anyone who could have built the plane. Give yourself the fastest speed any human being has ever travelled. That record belongs to the crew of Apollo 10, who touched about 39,897 kilometers an hour on their return from the Moon in 1969. At that speed, Proxima Centauri is about 115,000 years away. Not 115 years, 115,000. The fastest humans have ever moved gets you there in a span roughly a third as long as our species has existed. You can go faster than that, but only by cheating. The Parker Solar Probe holds the outright speed record for any object human beings have built. 692,000 kilometers an hour, or 192.2 kilometers every second, achieved on the 24th of December, 2024. That sounds like it ought to solve the problem. It does not, for 2 reasons. The first is arithmetic. Even at that speed, Proxima Centauri is about 6,600 years away, which is longer than the interval separating us from the first written language. The second reason is more interesting. Parker did not generate that speed. It fell. The probe was dropped down the sun's gravity well and picked up velocity the way a stone picks it up rolling downhill, and it reached its maximum at its closest approach, before climbing back out and slowing again. That speed is borrowed. It points inward rather than outward, and it cannot be carried away from the sun in any useful direction. If you want to compress the trip into something a person could survive, you have to talk in fractions of light speed instead, and the ladder is short. At 1% of the speed of light, Proxima Centauri is 425 years away. At 10%, 42.5 years. At 20%, a velocity nothing built by human hands has ever come within 4 orders of magnitude of, it is about 21 years. And at the speed of light itself, the absolute ceiling of the universe, it is 4.2465 years, and light does not carry passengers. You can already feel the shape of what is happening here. Every unit we try to use falls apart. Kilometers are too small to mean anything. Astronomical units become a number in the hundreds of thousands. Human speeds turn into geological epochs. And so people reach, almost by reflex, for a particular phrase to cover the gap. They say that a journey like that takes lifetimes. I want to flag that phrase now, and then set it down, and leave it alone for a while. When people say a journey takes lifetimes, they nearly always mean it as an exaggeration. It is a figure of speech, the way we say a queue took forever, or a meeting lasted an eternity. It is the thing you say when a number gets too large to feel. Remember that we said it. We are going to come back to it at the very end of tonight, and when we do, it is not going to be a figure of speech anymore. For now, let me hand you the one comparison that does the most work, because it involves something real, something built, something that exists and is still transmitting. Voyager 1 left Earth on the 5th of September, 1977. It is the most distant object human beings have ever made. Its engines have been silent since 1980. Everything it has done since then it has done by coasting, carrying forward momentum it stole from Jupiter and Saturn on the way past. It is currently moving away from the Sun at about 17 kilometers per second, which is roughly 38,000 miles an hour, and it has been doing that continuously for 49 years. On the 18th of November 2026 at 16 minutes past 2 in the morning Pacific time, Voyager 1 will reach a distance that no human object has ever reached. It will be exactly 1 light day from Earth, 16,094,799,096 miles, about 173 astronomical units. The distance light covers in 24 hours. It took 49 years and 2 months of unbroken flight to get there. Now recall that Proxima Centauri is 365.25 light days per light year, and it is 4.2465 light years away. Multiply those together and you get about 1,551 light days. Voyager 1 has spent 49 years covering one of them. At that rate, and it is not slowing down in any meaningful way, so the rate is fair, the journey to the nearest star would take somewhere in the region of 76,000 years. And here is the detail that turns that from a large number into something colder. Voyager 1 is not going to Proxima Centauri. It was never aimed there. Nothing we have ever launched has been aimed there. Voyager 1's closest future encounter with any star is a red dwarf called Gliese 445 in about 40,000 years, and it will pass that star at a range of roughly 1.6 light years. It will miss by a distance more than a third of the way to Proxima. So the honest position, before we have questioned anything at all, is this. The nearest star is 4.37 light years away. The fastest object we have ever released will take 49 years per light day, needs 1,550 of them, and is pointed somewhere else entirely. And all of that, everything I have just said, treats the number as though it were solid, as though 4.37 light years were a fact about the universe, fixed, measured, and settled. The same way the distance from London to New York is a fact. It is not. Over the next couple of hours I'm going to take that number apart in layers, and I am going to do it slowly because each layer is worse than the one above it, and I do not want you to miss any of them. We are going to find out that it is not one distance. We are going to find out that it is not a fixed distance. We are going to find out that our finest instrument for measuring distances cannot measure this one. We are going to find out that the star at the end of it has never been seen by a human eye. Not once, in the entire history of our species, and at the end of all of that we're going to arrive at the reason the trip will very likely never be made, and I promise you now, it is not the reason you are expecting. It has nothing to do with speed. It has nothing to do with fuel. Those are the two answers everybody gives, and they are both wrong. By the end of tonight, you will know exactly why the distance to Alpha Centauri is far worse than you think. But we cannot start there. We have to start somewhere much stranger and much quieter, and it begins with a question that sounds too simple to matter. Have you ever actually seen it? Most people, asked to point at the nearest star, would point at the sky and be wrong in 3 separate ways at once. I want to walk through all 3 because each one is a small crack, and the cracks are what this whole video is built out of. The first problem is geography. Alpha Centauri sits at a declination of about -60 degrees and 50 minutes. Declination is simply how far north or south of the celestial equator an object lies, and -60 degrees is a long way south. In practical terms, it means the system never rises above the horizon for anyone living north of roughly 29 degrees north latitude. Take a moment with the list of cities that puts on the wrong side of the line. London has never seen it. Neither has Paris, Berlin, Moscow, Beijing, Tokyo, Seoul, New York, Chicago, Toronto, Los Angeles, Madrid, Rome, Istanbul, Tehran, or Delhi. Cairo can just about scrape it along the southern horizon on a good night. Everyone north of that line, which is to say the substantial majority of the human population, and very nearly the entire history of European and Chinese and Middle Eastern astronomy, has lived their whole lives with the nearest star system permanently beneath the ground. That is a strange thought to sit with. The closest thing in the universe outside our own solar system, the one place we might conceivably reach, and most of us cannot look at it. Not with a telescope, not with binoculars, not on the clearest night of the year. It simply is not there. The Earth is in the way. For the minority who live far enough south, what they see is genuinely one of the finest things in the sky. Combined, Alpha Centauri shines at an apparent magnitude of about -0.27, which makes it the 3rd brightest star in the entire night sky, beaten only by Sirius and Canopus. Across the southern hemisphere it is known, together with Beta Centauri, as the Pointers, the pair of bright stars that indicate the way to the Southern Cross, and by extension the way to south itself, in a hemisphere that has no pole star worth the name. Southern navigators use them for centuries. In several Aboriginal Australian sky traditions, this region of the Milky Way is home to the emu in the sky, a figure formed not by stars but by the dark dust lanes between them, a constellation made out of absence, running right past the star we are discussing. There is a further wrinkle in that invisibility, and it is one of my favourite pieces of accidental history. The sky is not fixed. The Earth's axis wobbles slowly, completing one full circuit roughly every 26,000 years, and that wobble drags the whole celestial coordinate system with it. Alpha Centauri has not always been a southern star from the perspective of the northern latitudes. Several thousand years ago it climbed noticeably higher, and around 29,000 years ago it was visible from much further north than it is today. It is thought to appear in Ptolemy's catalogue in the 2nd century, but Ptolemy was working from Alexandria at 31 degrees north, where by his era the star had already slipped below the horizon. His entry appears to be inherited from older records or southern reports rather than from anything he observed himself. When Johann Bayer assigned the star its alpha designation in 1603, he had never seen it either. He was working from the accounts of southern voyagers. The nearest star system to Earth has, for essentially the whole span of written astronomy, been something northern astronomers catalogued on the word of somebody else. So a few billion people can see it, and to them it looks like one star. That is the second problem. Put a small telescope on Alpha Centauri and it splits cleanly into 2. It is one of the easiest and most satisfying double stars in the sky, and it has been known to be double since the Scottish Jesuit Jean Richaud noticed it in 1689 from Pondicherry while observing a comet. 2 suns, orbiting each other, which we will come back to in a while, because their relationship turns out to matter enormously. But here is the third problem, and it is the one I actually want you to carry out of this section. Neither of those 2 stars is the nearest star. The nearest star is a third member of the system, a red dwarf called Proxima Centauri. It is not next to the bright pair in the sky in any way that would strike you. It sits about 2 degrees away, which is 4 times the apparent width of a full moon, a noticeable gap, and it has an apparent magnitude of 11.13. That number deserves a moment. The magnitude scale runs backwards, so higher numbers mean fainter objects, and each step of 5 magnitudes is a factor of 100 in brightness. The faintest star a person with genuinely excellent eyesight can detect on a perfect moonless night, far from any town, is around magnitude 6. Proxima, at 11.13, is roughly 100 times fainter than that limit. It is fainter than Pluto at its brightest. It cannot be seen by a human being under any circumstances without optical aid. So let me say the thing plainly, because I think it is one of the strangest facts in astronomy, and it almost never gets said. No human being has ever seen the nearest star to the Sun. It has not happened once, not in 300,000 years of anatomically modern humans looking upward, not in the entire recorded history of astronomy across every civilization that ever kept records. Every ancestor who ever stood under the southern sky and wondered what those points of light were looked directly past it. The star closest to us, the one that would be the destination of the first journey we ever made out of our own system, is a thing our species has never actually laid eyes on. We did not even know it existed until 1915. It was found by Robert Innes, working at the Union Observatory in Johannesburg, and he did not find it by looking at it. He found it by comparing photographic plates taken at different times and noticing that one faint smudge had moved. Proxima has one of the largest proper motions of any star known, sliding across the sky at about 3.85 arcseconds every year, and that motion is the only reason anyone picked it out of a field of thousands of anonymous faint points. Its distance was not pinned down for another couple of years, and only then did it become clear that this unremarkable 11th magnitude dot was, in fact, the closest star in the sky. It was named Proxima, the nearest one, and it kept the name. That proper motion is worth pausing on, because it is going to become important later in a way that will not be comfortable. The bright pair, Alpha Centauri A and B, slide across the sky at about 3.71 arcseconds a year. An arcsecond is 1/3600th of a degree, so that is a tiny amount. You would need a good instrument and a decade of patience to notice. But it accumulates. At 3.71 arcseconds a year, the system crosses a distance equal to the apparent width of the full moon in roughly 480 years. The stars in the sky are not a backdrop. They are traffic, moving slowly enough that a human lifetime cannot see it, and a civilization can. There is a small, sharp irony buried in this. Alpha Centauri A, the brighter of the two suns in the pair, is very nearly a twin of our own. It is a G-type dwarf of about 1.079 solar masses, with roughly 1.5 times the sun's luminosity, and if you swapped it with our sun, the difference would be noticeable but not dramatic. It is the most sun-like star in our neighbourhood by a comfortable margin. If you moved our own sun out to Alpha Centauri's distance, it would appear as a magnitude 0.5 star. Comfortably visible, one of the brighter things in the sky, but nothing anyone would write about. That is what we look like from there. A moderately bright star, unremarkable, one of a few hundred you could name. Anybody standing on a planet in that system, looking back toward us on a clear night, would see the sun as a fairly ordinary point of light in the constellation Cassiopeia, which incidentally would have a 6th star in it from that vantage, turning the familiar W into something a little more crooked. That is the whole relationship. From here, our nearest neighbour is invisible to 2/3 of humanity, and its closest member has never been seen at all. From there, we're a mildly interesting dot in someone else's constellation, and yet the number holds, 4.37 light-years. It sits there in every reference, calm and unchanged, describing a place most of us cannot look at, containing a star nobody has ever seen. That raises a question I think you should be asking by now, and it is a fair one. If we cannot see it, and most of us cannot even find the part of the sky it is in, then how do we know how far away it is at all? The answer to that question involves a triangle, a human hair, and a man who worked out the correct answer 6 years before anybody else, and then could not bring himself to tell a single person. The method for measuring the distance to a nearby star is the simplest idea in astronomy, and for 200 years it was the single hardest thing anyone had ever tried to do. Hold up a finger at arm's length and close one eye, then swap eyes. The finger jumps against the background. It does not move. You moved, and the shift you see is a function of how far away the finger is. Bring it closer, and the jump gets larger. Push it further away, and the jump shrinks. If you knew the distance between your two eyes, and you could measure the angle of the jump precisely, You could work out the distance to your finger without ever touching it. That is triangulation, and it is the oldest surveying technique there is. Now scale it up. Your two eyes become the Earth in January and the Earth in July. The gap between them is not 7 centimeters, but 2 astronomical units. About 300 million kilometers, the full diameter of our orbit, and the finger becomes a star. Observe a nearby star in the winter, observe it again 6 months later, and it should appear to shift very slightly against the far more distant background stars. Half of that annual shift is what astronomers call the parallax angle, and from it the distance falls straight out of basic trigonometry. That is the whole idea. It requires no assumptions about how stars work, no models of stellar physics, no theory of anything. It is a triangle, and that is what makes it, even today, the foundation of every distance in the universe. Every other method we have is ultimately calibrated against it. So why did it take until 1838? The answer is the size of the angle. Alpha Centauri's parallax is 0.747 arcseconds. To translate that into something you can picture, it is the apparent width of a human hair, about 1/10 of a millimeter thick, viewed from 28 meters away. That is the largest such angle in the sky, apart from Proxima's 0.768. Every other star in the universe is a smaller shift than that. Most are far smaller. For 2 centuries, the failure to detect any parallax at all was the single strongest empirical argument against the idea that the Earth moves. Tycho Brahe raised the objection in the 1580s, and it was a good objection. If the Earth genuinely swings 300 million kilometers from one side of its orbit to the other, the nearby stars ought to shift, and they stubbornly did not. The resolution, when it came, was not that the Earth stands still. It was that the stars are unimaginably further away than anybody had been willing to seriously entertain, so far away that the entire orbit of our planet is a baseline too short to matter. The attempts piled up, and so did the retractions. Robert Hooke published a parallax for Gamma Draconis in 1674 and was wrong. John Flamsteed claimed one and was wrong. James Bradley hunted parallax between 1725 and 1728, failed to find it, and instead accidentally discovered the aberration of starlight, the tiny tilt in a star's apparent position caused by the Earth's own motion through the path of the incoming light. It was the first direct observational proof that we are moving, and it was a consolation prize for a man who had gone looking for something else entirely. By the 1830s, the field had a reputation. Announcing a stellar parallax was a good way to end a career. It is worth knowing what Bessel actually used, because the instrument is half the story. A heliometer is a telescope whose objective lens has been sawn cleanly in half, with the 2 halves mounted so that one can slide against the other. Sliding them makes 2 images of the field, and by moving one image until a chosen star sits exactly on top of another, you can read the angular separation between them off a precision screw. It was originally built to measure the diameter of the Sun, which is where the name comes from. Bessel took an instrument designed for the biggest thing in the sky and turned it on the smallest measurable angle anyone had ever attempted. He also chose his target well. 61 Cygni was known as the flying star because of its rapid proper motion, the same clue that had pointed Henderson at Alpha Centauri. Nobody could see how far away the nearby stars were, so they used how fast the stars appeared to move as a proxy for closeness, and the proxy worked. There was a third competitor too, and he is usually left out. Friedrich Georg Wilhelm Struve, at Dorpat, published a parallax for Vega in 1837, a year before Bessel. But Struve revised his own figure heavily and repeatedly, and the astronomical community, burned too many times, did not accept it. 3 men, on 3 continents' worth of separation, converged on the same impossible measurement within about 18 months of one another, after 2 centuries of total failure. That is what a technique looks like at the exact moment it becomes possible. That brings us to Thomas Henderson. Henderson was a Scottish lawyer's clerk who had taught himself astronomy well enough to become genuinely good at it, and in 1831 he was appointed His Majesty's astronomer at the Cape of Good Hope. He did not want the job. He took it anyway, arrived in April 1832, and proceeded to be thoroughly miserable for the entire duration of his posting. He disliked the heat. He disliked the damp. He disliked the administration, and the administration disliked him. What he did have was the southern sky, an instrument, and one specific piece of advice. A colleague had suggested that Alpha Centauri was an unusually promising target because it had an enormous proper motion, It was visibly sliding across the sky faster than almost anything else, and large proper motion tends to indicate a nearby star. So Henderson watched it, night after night, timing its passage across the wires of his transit instrument through 1832 and 1833. Then he went home. Picture the room. It is the observatory on a low-rise outside Cape Town, and it is late, and the air is thick and warm and does not cool the way it does in Scotland. Table Mountain is a flat absence against the stars behind the building. The transit instrument is a long tube fixed to swing only in one plane, north to south, and the work is monotonous. Wait for the star to drift into the field, call the moment it crosses each wire, write the numbers down, do it again tomorrow. Henderson has been doing this for months. He is tired of the Cape and he is going to resign. But now he is at a table with the reductions in front of him, and the numbers have resolved into an angle, and the angle is about 1 arcsecond. He knows exactly what that means. He works the trigonometry, a lawyer's clerk's careful arithmetic, and it comes out at something in the region of 3 light years, a distance to a star, an actual, measured, triangulated distance to another sun, the first anyone has ever obtained. He sets the page down. He does not shout. There is no one to shout to, and what he feels, sitting there with the first stellar distance in human history under his hand, is not triumph, it is doubt, because he knows the list. He knows Hooke and Flamsteed and every confident man who published a parallax and was quietly dismantled for it within the decade. He knows his instruments are not the finest in the world. They are the ones the Admiralty could spare for the Cape, and he knows that if he is wrong about this in public, that is the whole of what he will be remembered for. So he packs the observations into his trunk, and he sails home to Scotland, and he does nothing. He does nothing for 6 years. He reduces the data slowly. He writes to his successor at the Cape asking for confirming observations, and waits for them to arrive by ship. He becomes the first Astronomer Royal for Scotland in 1834, and in the meantime, on the other side of Europe, Friedrich Wilhelm Bessel at Königsberg points a Fraunhofer heliometer at a dim, fast-moving star called 61 Cygni, and in December 1838 announces a parallax of 0.3136 arcseconds, a distance of about 10.5 light-years. It is the first stellar parallax ever published. It holds up beautifully. The modern value is within a few percent of Bessel's. Henderson read his own paper to the Royal Astronomical Society 2 months later, in January 1839. He had been first by 6 years, and he was second by 9 weeks. I want to leave that where it is for a moment, because the shape of it matters more than the trivia. Thomas Henderson was the first human being to correctly measure how far away another star is, and he could not bring himself to say so. He was not a coward. He was a careful man in a field that had spent 200 years humiliating careful men, and he chose caution, and caution cost him the thing he had actually done. And there is a final turn of the knife in it that almost nobody mentions. Henderson's measured parallax was about 1 arcsecond. The true value is 0.747. His angle was too large, which means his distance was too small. The number that frightened him into silence was not far enough away. The real distance was worse. It has been worse every single time anyone has looked closer, and that is going to become something of a pattern tonight. There is one more thing to say about parallax before we move on, and it is the piece that tells you how our whole vocabulary was built around a problem we could not solve. Astronomers eventually defined a unit specifically for this work. A parsec is the distance at which a star would show a parallax of exactly 1 arcsecond, and it comes out at 3.26 light-years. The unit was invented to describe the close stars. There is not a single star in the sky close enough to qualify, not Proxima, at 0.768, not Alpha Centauri, at 0.747, nothing. The unit built to measure our neighbourhood has no members in it at all, and even that is not the strangest thing about the distance we're chasing, because we still have not established what the distance to Alpha Centauri actually refers to. The sentence is the distance to Alpha Centauri, and there is a false premise buried inside it that almost nobody notices, because the sentence is grammatically fine and the false premise is astronomical rather than linguistic. Alpha Centauri is not a star. It is 3 stars, and they are not in the same place. Start with the 2 you can see. Alpha Centauri A carries the formal name Rigil Centaurus, from the Arabic for the foot of the centaur. It is a G-type dwarf of about 1.079 solar masses a little larger and a little hotter than our Sun, radiating about 1.5 times as much light. Alpha Centauri b has the formal name Ptolemy. It is a K-type dwarf of about 0.909 solar masses, cooler and more orange, radiating about half as much light as the Sun. These two are locked together. They orbit a common centre of mass with a period of 79.91 years, near enough to a human lifetime that a person born at one point in the orbit could, in principle, live to see it complete. The orbit is not a circle. Its eccentricity is about 0.518, which is high, and the semi-major axis is about 17.57 astronomical units. In practice, that means the two stars swing from about 11.2 astronomical units apart at their closest to about 35.6 at their widest. Translate that into our own system, and the picture becomes strange. Imagine a second sun in our sky that spends part of its 80-year cycle just inside Saturn's orbit, and the rest of it swinging out past Neptune and back again. Not a distant point of light. A second sun, close enough at its nearest approach to be a disk, dimming and brightening across a human lifetime. That eccentric waltz has a consequence that matters for anyone thinking about what might be there. When two stars orbit each other at 11 to 36 astronomical units, their combined gravity carves the available real estate down hard. Planets can only hold stable orbits fairly close in to either star. The modelling generally gives you about 2 to 3 astronomical units of usable space around each one before the other. Stars' pull starts stripping orbits apart over long time scales, which means that if there are planets in the Alpha Centauri system around the bright pair, they are inner system planets by necessity. There is no room for a Jupiter out there. There is no room for a Saturn, or a Neptune, or an Oort cloud in the sense we have one. The architecture of that system, whatever it turns out to be, is compressed into the inner few astronomical units by the presence of a second sun. Now add the third star, and this is where the arithmetic starts to come apart. Proxima Centauri is gravitationally bound to that pair, but it does not orbit close to them. It sits at a distance of roughly 13,000 astronomical units from the AB pair. 13,000. For comparison, Neptune orbits our Sun at 30 astronomical units, and Voyager 1, after 49 years, is at about 173. Proxima is more than 400 times further from its parent pair than the most distant object we have ever built is from our Sun. In light years, that separation is about 0.21. Sit with that number, because it is the first genuinely uncomfortable thing in this section. The distance between the nearest star and the next nearest star is about 0.21 light-years. The distance from us to the whole system is about 4.3, which means that the internal spread of the Alpha Centauri system, just the gap between its own members, is roughly 5% of the entire journey there. You cannot go to Alpha Centauri, you have to pick one, and the two options are genuinely different distances. Proxima Centauri sits at 4.2465 light-years. Alpha Centauri A and B sit at 4.365 light-years. The gap between those two figures is about 0.12 light-years, which sounds trivial until you convert it. It is about 1.1 trillion kilometers, or roughly 7,500 astronomical units. The difference between the two headline answers to how far is Alpha Centauri is itself about 250 times the width of our entire planetary system out to Neptune. That is the rounding error inside 4.37. Proxima's orbit around the pair, incidentally, takes something on the order of 547,000 years to complete. That is not a typo, and it is not a rounding of 547. It is more than 500,000 years for one lap, which means that Proxima's position, including whether it is the nearest of the three to us at all, changes over spans that make the whole of human history a rounding error. Proxima is currently the closest. It is not permanently the closest. It holds the title for a stretch of its orbit and then hands it back. So the nearest star is not merely a thing nobody has seen. It is a temporary appointment. There is a related fact that puts the whole idea of a fixed nearest star into perspective, and it involves something that has already happened. About 70,000 years ago, a small red dwarf binary now catalogued as Schultz's star passed through the outer edge of our solar system. Reconstructions of its trajectory put its closest approach at somewhere around 0.8 light-years from the Sun, considerably closer than Proxima is today. Anatomically, modern humans were alive and looking at the sky. That star would have been too faint to notice most nights, but red dwarfs flare, and during a flare it may have become briefly visible as a dim red point that had not been there the night before. Something came closer to us than the nearest star currently is. Our ancestors could very nearly have watched it happen, and it left again. In roughly 1.3 million years, a star called Gliese 710 is projected to pass within about 0.17 light-years, close enough to be, briefly by a wide margin, our nearest neighbour, and close enough to stir the outer comet reservoir on its way through. Now here is the part I have been building toward, and it is the layer that I think is genuinely the strangest fact in this entire subject. Those two distances I just gave you are measured by two different instruments, using two different techniques, because no single instrument can do both. Proxima's distance comes from Gaia, the European Space Agency's astrometry mission, which is without exaggeration the finest instrument for measuring positions and distances that our species has ever constructed. Gaia has fixed the parallaxes of more than 1.4 billion stars at precisions measured in microarc seconds, millionths of an arc second. It has built a three-dimensional map of our galaxy that would have been science fiction 30 years ago. Its parallax for Proxima Centauri is about 768.1 milliseconds, and that is where 4.2465 light-years comes from. Gaia cannot measure Alpha Centauri A or B. They are too bright. Gaia's detectors are built for the general stellar population, and a star of magnitude minus 0.01 saturates them completely. It floods the pixels and the position information is destroyed. The most precise astrometric instrument ever built, an observatory that has surveyed more than 1 billion stars, is blind to the two brightest members of the nearest star system, for the specific reason that they are near enough to be bright. So the AB distance comes from somewhere else entirely. The figure we use, a parallax of about 747.17 milliseconds, giving 4.365 light-years, with an uncertainty of around 0.003 of a light-year, comes from ground-based work by Pierre Cavella and colleagues, published in 2017, using the Very Large Telescope and the New Technology Telescope in Chile. Careful, painstaking, ground-based astrometry. The same fundamental technique Henderson was using at the Cape in 1832, with 185 years of refinement bolted onto it. We went to the trouble of putting a billion-star surveyor into orbit at a Lagrange point, and for the nearest star system to the Sun, we still have to do it from the ground. And even that beautiful modern uncertainty deserves unpacking, because 0.003 of a light-year sounds like precision, and is not. 0.003 of a light-year is about 28 billion kilometers. It is nearly 200 astronomical units. Our best number for the distance to the nearest Sun-like star has an error bar longer than the distance from here to Voyager 1. So let me restate the sentence honestly, with everything we now know folded back into it. The nearest star system is either 4.2465 or 4.365 light-years away, depending which of its three stars you mean. The gap between those answers is 7,500 astronomical units. The two figures were taken by two different instruments because the better one cannot see the brighter stars. The closest of the three is only temporarily the closest, and the error bar on the best of it is 200 times the width of the Earth's orbit. That is what 4.37 light-years is compressing, and every one of those problems is a problem of knowledge, of what we can measure and what we cannot. None of them touches the actual journey, because there is a much worse problem waiting, and it is this. Even if you fixed all of it, even if you knew the distance perfectly to the meter, you still could not aim a ship at it. The star will not be there when you arrive. Alpha Centauri is coming toward us. It is not coming dramatically, and not on any schedule that concerns anyone alive. But the system's radial velocity, its motion directly along our line of sight, is about minus 22 kilometers per second, and the minus sign means closing. Every second, the nearest star system gets 22 kilometers nearer. Every year, about 700 million kilometers nearer. That is roughly 4.5 times the distance from the Earth to the Sun, every year, for free. Follow that forward. Combining the radial approach with the system's sideways motion, the closest approach to the Sun works out at somewhere around the year 27,000 of the Common Era, at a separation of roughly 3 light-years. The published estimates cluster between about 2.9 and 3.2, depending on which proper motion solution you use. Now think about what that means as a travel problem, because it is genuinely one of the more disorienting ideas in interstellar planning. If you did nothing at all, built nothing, launched nothing, spent nothing, and simply waited about 25,000 years, the distance to Alpha Centauri would fall by roughly 30%. Not because of any technology, Because the destination came to you. 30% of the hardest journey anyone has ever contemplated, in exchange for patience. And the reason this is worth stopping on is not the free discount. It is what it does to the concept. It means the distance to Alpha Centauri is not a property of the universe. It is a property of when you ask. There is no number that is simply true. There is only a number that is true for a departure date, and the number changes underneath you while you are deciding. Keep going forward past the closest approach and it gets stranger. After roughly the year 27,000, the system begins receding again, and by around 100,000 years from now, Alpha Centauri will no longer be our nearest neighbour at all. Ross 248 and Gliese 445 take their turns as the local stellar traffic reshuffles, each holding the title for a stretch of a few thousand years and then losing it. On a long enough view, the nearest star is not a place, it is a queue. It is worth saying where these velocity numbers come from, because the technique is elegant, and it is the same physics that runs the rest of cosmology. Radial velocity is measured from the spectrum. Every element absorbs light at specific known wavelengths, and those absorption lines appear as dark gaps in a star's spectrum at positions fixed by atomic physics. If the star is moving toward you, every one of those lines shifts very slightly toward the blue end. If it is moving away, they shift toward the red. Measure the shift and you have the speed along the line of sight, to a precision that modern spectrographs push down to meters per second. It works at any distance, and it does not care how bright the star is. So we can tell you Alpha Centauri's approach speed far more confidently than we can tell you its distance. The one thing Gaia cannot get is the one thing that requires the star to be well behaved on a detector. The sideways component is harder, and it is measured a completely different way, by simply photographing the star's position year after year and watching it walk. That gives you an angle per year, and to turn an angle per year into a speed in kilometers per second, you must already know the distance. The two measurements are entangled. The full space velocity of Alpha Centauri relative to the Sun, once you combine both components, comes out at about 32 kilometers per second, roughly twice as fast as Voyager 1 is leaving us, in a system that weighs about 2 solar masses. But the radial approach is only half of the motion, and the other half is where the practical nightmare lives. The Alpha Centauri pair has a proper motion, a sideways drift across our sky, of about 3.71 arcseconds per year. That is among the largest of any bright star. It is also, on any human timescale, unnoticeable. Over a lifetime it amounts to about 4.5 arc-minutes, which is a shift you would need instruments to detect. Over a mission, it is catastrophic. Do the arithmetic honestly. Over a 100-year transit, 3.71 arcseconds a year accumulates to 371 arcseconds, about 6 arc-minutes, roughly a fifth of the width of the full moon. Over a 1,000-year transit it is more than a degree, twice the moon's width, and over Voyager 1's 76,000 years, the accumulated proper motion comes to something like 282,000 arcseconds. That is approaching 80 degrees of arc. A Voyager-class probe aimed at Alpha Centauri would not be launched toward Alpha Centauri. It would be launched toward a completely different empty region of sky, nearly a quarter of the way around the celestial sphere from where the star presently appears, on the understanding that the star will get there eventually and the probe will get there at approximately the same time. Now let me put you at the console, because I think this is one of the moments where the abstraction needs a body. You're looking at a target designation on a screen. The screen shows a star, and the star is a lie in 3 separate ways at once, and you have to correct for all 3 simultaneously. The first lie is time. The light making that dot on your display left Alpha Centauri 4 years and 3 months ago. You're not looking at the star, you're looking at a recording of the star, and everything in it, the position, the brightness, the state of both suns, is 4 years stale. The current whereabouts of that system is something no instrument on Earth has any information about at all and never will. The second lie is approach. The system is closing on you at 22 kilometers a second while you sit here. So the distance you calculated when you started the calculation is already wrong by the time you finish it. Not by much, by a few million kilometers. But the correction never stops. The third lie is drift. The whole system is sliding sideways at 3.71 arcsecons a year, and your ship will take decades or centuries or millennia to cross, and you must lead the target by exactly that much. The way a hunter leads a bird, except the flight time is measured in generations and the bird is a sun. And here is your tolerance. At 4.2465 light-years, An aiming error of 1 single arc second puts you off by about 195 million kilometers. That is more than the distance from the Earth to the Sun. 1 arc second, 1/3600th of 1 degree, an angle so small that atmospheric turbulence alone smears ground-based images by several times that much on a good night. And you miss by more than an astronomical unit. You are threading a target region of a few tens of astronomical units, at a range of 268,000 astronomical units. That is a precision of roughly 1 part in 10,000, sustained over a flight time longer than any institution has ever existed, with no possibility of a course correction based on advice from home. Take your hands off the console. Nobody has ever had to solve this problem, because nobody has ever come close enough to needing to. For scale on how routine this kind of aiming is at solar system ranges, consider that navigating a spacecraft to Pluto, a target 3 billion miles away, moving at about 4.5 kilometers a second, required course corrections right up to the final months, and New Horizons still arrived inside a target window measured in tens of seconds after a 9.5-year flight. That was an extraordinary piece of navigation, and it was done with continuous two-way radio contact, ongoing optical tracking of the target, and a team that stayed employed for the whole trip. Every one of those 3 advantages disappears at interstellar range. You cannot track the target usefully from the ship, you cannot get advice from home in under 8 years, and the team does not stay employed because the team does not stay alive. And there is a final complication layered over all of that, which is that the 27,000 CE closest approach figure is itself only approximate. Both stars are moving through a galaxy that is full of other masses. Passing stars perturb trajectories. Giant molecular clouds perturb trajectories. The galactic tide, the differential pull of the Milky Way's own mass distribution, is slowly working on both of us. Over 25,000 years those effects are small but not zero, which means the future distance to Alpha Centauri is not merely variable, it is uncertain in a way that compounds the further ahead you look. So we now have a distance that is not one number, was not measured by our best instrument, describes a star nobody has seen, is shrinking at 700 million kilometers a year, will stop shrinking and start growing in 25,000 years, and requires you to aim at empty sky with a precision nobody has ever demonstrated. And I want to be very clear about something. Not one of those problems is the reason the trip will probably never happen. Every one of them is, in principle, solvable. You can measure better, you can compute the lead angle, you can pick a launch date. The thing that actually stops this is still coming, and we are not ready for it yet, because there is one more failure I want to show you first. The failure of your own imagination. Because I have been giving you numbers for half an hour, and I would bet almost anything that you cannot picture a single one of them. There is a good reason for that, and it is not a fault in you. Human beings are good at scale models. It is one of our better tricks. We shrink a thing until it fits inside a room, and the shrinking preserves the relationships, and suddenly a person who cannot picture the solar system can picture the solar system. Interstellar distance is the point where the trick stops working, and I want to show you the exact moment it breaks, because the breaking is informative. Put the sun on a table in front of you as a grapefruit, 10 centimeters across. That is a shrinking factor of about 14 billion to 1, which sounds severe but produces a solar system you can actually walk around. At this scale, Mercury is a grain of dust 4 meters from the table. Venus is a slightly larger grain at 7.5 meters. The Earth is a coarse grain of sand, 1 millimeter across, 10.5 meters away, the far side of a large room, or the width of a suburban garden. The Moon is a speck of dust orbiting that grain of sand at a distance of about 2.5 centimeters. Every human being who has ever left the Earth's atmosphere has travelled less than the width of your thumb from that grain. Mars is another dust grain at 16 meters. Then a long empty stretch, and Jupiter appears as a peppercorn, about a centimetre across, 55 metres out, further than most gardens. Saturn is a smaller peppercorn at 100 metres, Uranus at 200 metres. Neptune, the outer planet, is a small seed about 315 metres from the table, a 5-minute walk. Voyager 1, after 49 years of continuous flight at 17 kilometres a second, is about 12 kilometres from the grapefruit. Hold that. 12 kilometres. On a scale where the entire planetary system fits inside 300 metres, the most distant object our species has ever built is across town, a couple of hours' walk or a short drive. 49 years of flight has bought us a trip to the other side of a city. Now walk to the next grapefruit. It is 2,870 kilometers away. Put the first grapefruit in New York and the second one is past Denver. Put it in London and the second one is in the Sahara, south of the Atlas Mountains. Put it in Sydney and the second one is in the middle of the Indian Ocean. And in between, this is the part that matters, there is nothing. Not a grain of sand, not a speck of dust, 2 grapefruits, and 2,870 kilometers of completely empty road. So imagine actually doing it. At the scale of the model, you leave the table with the grapefruit on it. You walk past the sand grain that is the Earth, 10 meters out. 20 minutes later, you pass the seed that is Neptune. An hour into your walk, you are 3 or 4 kilometers out, and the entire solar system is behind you, and everything that has ever happened to every human being who has ever lived happened inside the first 300 meters. You keep walking. By the end of the first day, you have done perhaps 30 kilometers. You have passed Voyager 1 somewhere in the morning and you have gone twice as far again. The grapefruit is long out of sight. Nothing has changed in your surroundings, because there is nothing in your surroundings to change. By the end of the first month, you have walked 900 kilometers. You are a third of the way. Nothing ahead, nothing behind. And if the model were honest, there would be no ground under you, no air, no light except 2 impossibly distant points, one of which you cannot see because the second grapefruit is not the nearest object. The nearest object is a dim red marble somewhere off to the side, and at this scale it is about the size of a peppercorn, and it is still 140 kilometers short of the 2 suns. 3 months of continuous walking, that is the model. That is what the emptiness between 2 neighbouring stars looks like when you compress the entire solar system into 300 meters. And here is the arithmetic that makes the model useful rather than merely pretty. The ratio between the size of our planetary system and the distance to the nearest star is about 9,000 to 1. That is why every scale model of the solar system you have ever seen, every museum floor, every planet walk trail, every classroom poster, stops at Neptune. Not because Neptune is the edge of anything, because the next object is 9,000 times further out than the whole model, and there is no building, no park, and no country large enough. Try it at a different scale and the failure repeats identically. Shrink the sun to a single grain of sand 1 millimeter across. Now the Earth is a microscopic speck 11 centimeters away. The whole planetary system fits comfortably on a dinner plate, and the nearest star is a second grain of sand 29 kilometers down the road. Dinner plate, 29 kilometers. Every scale you choose gives you the same shape, a system you can hold, and a neighbour you cannot reach on foot in a day. There is a version of this failure that has been quietly embarrassing museums for decades, and it is worth knowing about because it shows the problem is structural rather than a lack of ambition. Sweden built a scale model of the solar system at a ratio of 20 million to 1, using the Ericsson globe in Stockholm, 110 meters across, as the Sun. At that scale, the planets are spread across most of the length of the country, with the outer solar system objects sited in towns hundreds of kilometers north of the capital. It is one of the largest permanent scale models in the world, an entire nation used as an exhibit. And at that scale, the nearest star would be roughly 2 million kilometers away, which is about 5 times further than the actual moon. The model that consumed a country cannot reach a neighbour without leaving the planet. The same thing happens in reverse when people try to model the distance directly. If you scale the distance to Proxima Centauri down until it fits across an average living room, say 5 meters, then the Sun and Proxima both become objects about 1/7 of a millimeter across, barely visible specks, and the entire solar system out to Neptune is a smudge you would need a magnifier to resolve. There is no scale at which both the journey and the destination are visible at once. Either you can see the places or you can see the gap, never both. That is not a limitation of models, it is a fact about the ratio, and the ratio is the story. This is the reason the numbers do not land. It is not that 4.37 light-years is a big number. Human beings deal with big numbers constantly. It is that there is no shared human experience with this ratio in it. Everything we have ever built our intuitions on, journeys, oceans, continents, the sky itself, is a world where things are separated by amounts you can traverse by continuing to do the same activity for longer. Interstellar space is not that. It is a world where the emptiness is the dominant feature and the objects are the rounding error. Let me step back for a moment and put the pieces together, because we have covered a lot of ground and I want the picture to be complete before we go further. We started with a clean number, 4.37 light-years. We found that most of humanity cannot see the system it describes, and that its closest member has never been seen by any human being in the history of the species. We found that the number was first measured by a man who was too cautious to publish it, in a field that had been failing at the measurement for 200 years, and that his answer was too small. We found that it is not one number but two, taken by two different instruments, because our best instrument is blind to bright stars. We found that the system's own internal spread is 5% of the journey. We found that the number is shrinking, will start growing again, and cannot be aimed at without leading the target by degrees of arc. And now we have found that it cannot be modelled, at any scale, by any means, in any building on Earth. Every single one of those is a problem with the number. None of them is a problem with the trip. So far, we have only been talking about how far away it is. We have not yet talked about what happens when somebody actually tries to go, and we have in fact tried. We have built things and thrown them, hard, with everything we have. I want to show you how far they got. There are exactly 5 objects made by human beings that are leaving the solar system permanently. 5. That is the complete list, after 70 years of spaceflight. Pioneer 10, launched in 1972. Pioneer 11, 1973. Voyager 2, August 1977. Voyager 1, September 1977. And New Horizons, launched in 2006 on its way to Pluto. Both Pioneers went silent decades ago. Pioneer 10's last faint contact was in 2003, and they are still out there, coasting, dead, on trajectories that will not bring them back. Not one of those 5 is aimed at a star. I want to be careful here, because that fact is often reported as though it were a strange oversight, and it is not. It is a consequence of geometry, and the geometry is worth understanding because it explains something structural about our situation. Every one of those 5 objects got the bulk of its speed the same way, not from its engines, but from planets. A gravity assist works by flying a spacecraft close past a moving planet so that the planet's gravity swings it around, and because the planet is itself orbiting the Sun at enormous speed, the spacecraft leaves the encounter carrying away a share of that orbital momentum. It is, in a very literal sense, stealing velocity from a world. Jupiter gave Voyager 1 most of what it has. The planet slowed down by an amount too small to measure in exchange. This is the only technique we have that produces solar escape velocities with existing rockets, and it comes with a hard constraint. The planets all orbit close to a single plane, the ecliptic, tilted by only a few degrees from one another, so every gravity assist we can perform throws the spacecraft out along or near that plane. Alpha Centauri sits about 60 degrees below it. There is no route. There is no planet in the right place to swing a probe southward out of the ecliptic and toward the nearest star. Getting there would mean either building up the velocity from propulsion alone, which, as we are about to see, the physics forbids for any chemical rocket, or performing a plane change, which is one of the most expensive maneuvers in all of orbital mechanics. The free rides all go the wrong way. It is worth appreciating how narrow the window was for even the assists we did get. The Voyager missions exploited an alignment of Jupiter, Saturn, Uranus, and Neptune that permits a single spacecraft to chain gravity assist from all 4. And that alignment recurs roughly once every 176 years. The 1970s happened to be one of those windows. Had the space age begun 40 years later, Voyager 2's grand tour would not have been possible at all, and our most distant objects would be substantially closer than they are. Our entire interstellar reach, such as it is, rests on a planetary coincidence that we happen to be technologically ready for. So where are they going instead? Nowhere in particular, and that is the honest answer. Voyager 1 is heading toward the constellation Camelopardalis and will pass within about 1.6 light-years of a red dwarf called Gliese, 445 in roughly 40,000 years. Voyager 2 will pass within about 1.7 light-years of Ross 248 in a similar span. Pioneer 10 is drifting toward Aldebaran and will take something over 2 million years to arrive in that general direction. These are not encounters. A miss of 1.6 light-years is more than a third of the distance we have been discussing all evening. It is like saying a ship crossing the Atlantic will pass within 1,000 kilometers of Iceland, and the speeds themselves deserve to be looked at squarely, because they are the actual measure of our reach. Voyager 1 is doing about 17 kilometers per second relative to the Sun. Voyager 2 about 15.5. New Horizons, which left Earth faster than any spacecraft in history at launch, is doing about 13, and will never catch either Voyager, because it got only one substantial gravity assist and the Voyager's got several. Pioneer 10 and 11 are slower still. 17 kilometers per second is roughly 61,000 kilometers an hour. It is about 50 times the speed of a rifle bullet. It is fast enough to cross the United States in under 4 minutes, and it is 1/10,000th of 8% of the speed of light, which is to say, it is nothing at all. There is a comparison I find genuinely humbling here. The Sun itself is moving. It orbits the center of the Milky Way at roughly 230 kilometers per second, carrying the entire solar system with it, completing one circuit every 230 million years or so. That is more than 13 times Voyager 1's speed. The star we are trying to escape is travelling more than 13 times faster than our fastest escape. Everything we have ever launched is a small deviation on top of a much larger motion that we did not generate and cannot control. In a real sense, the Sun is not being left behind. It is dragging the whole neighbourhood, including our probes, around a galaxy, and our contribution to the trajectory is a rounding error on the Sun's. There is a further detail about Voyager 1 that I think is the quietest and most affecting thing in the whole fleet's story. Its engines stopped firing in 1980. Everything the spacecraft has done for the last 46 years, every kilometre of the 25 billion it has covered, it has done by coasting. It is not being propelled, it is not accelerating, it is simply continuing, in the way that objects in a vacuum continue, because nothing has been in the way to stop it. Its power comes from a radioisotope thermoelectric generator, a block of plutonium dioxide whose natural decay heat is converted directly into electricity. That block is running down at a little under 1% a year, and it has been running down since 1977. Instruments have been switched off one at a time, in a carefully planned order, over decades, to keep the remaining ones alive. By the early 2030s there will not be enough power left to run anything, and the spacecraft will go quiet, and it will keep going anyway, silently, for the next several billion years, long after everyone involved in building it is gone, and long after the plutonium has decayed to nothing. It will still be moving, it will simply have stopped being able to tell us about it. Now let me bring this back to the number, because there is one more piece of the Voyager story that I think is the cleanest illustration in the whole subject. On the 18th of November this year, Voyager 1 reaches 1 light day from Earth, 16,094,799,096 miles calculated to the second. 49 years and 2 months of flight. It is a genuine milestone and it deserves the attention it will get. Now consider what that milestone means for communication, because this is where it stops being abstract. From that day forward, a command sent from Earth takes 24 hours to arrive, and any acknowledgement takes 24 hours to come back. If an engineer at the Deep Space Network says good morning to Voyager on a Monday, the reply arrives on Wednesday. The data rate at that distance is about 160 bits per second, slower than a modem from 1980. The signal arriving at Earth from Voyager's 22-watt transmitter is measured in attawatts. The accumulated energy received from Voyager across the entire mission would not light a small bulb for a fraction of a second. That is 1 light day. Proxima Centauri is 1,551 of them, and the inverse square law is not kind about that. Received power falls as the square of the distance, so a transmitter at Proxima's range delivers something like 2.4 million times less power than the same transmitter at Voyager's range. The 160 bits per second link that already requires a 70-metre dish, and cryogenically cooled receivers would need to be something else entirely, several million times better, before a whisper from Alpha Centauri became a sentence. So here is the position, stated plainly, with nothing rhetorical in it. Human beings have launched 5 objects that will leave the solar system. The fastest is doing 17 kilometers per second, took 49 years to cross 1 light day, is heading in a direction from which the nearest star cannot be reached, will miss its closest stellar encounter by a third of the distance we are discussing, and is moving 13 times slower than the star it left. That is our reach. That is what 7 decades of spaceflight and every rocket humanity has ever fired adds up to, measured against this one distance. And you might reasonably say, fine, but those are old machines built with 1970s technology, and we could obviously do better if we tried. We could. Somewhat. But there is a piece of mathematics standing in the way that is not about technology at all, and it does not care how clever the engineers are, and it is the reason every serious study of interstellar flight in the last 60 years has arrived at roughly the same set of unhappy conclusions. It is an equation written in 1903, and it eats ships. Konstantin Tsiolkovsky was a deaf schoolteacher in a small Russian town who worked out the mathematics of spaceflight decades before anyone had built an aircraft. In 1903 he published the relation that still governs every rocket ever built, and it is a short, unassuming piece of algebra that has quietly killed more Starship designs than any other single idea in physics. The principle is simple. A rocket moves by throwing mass backwards. The speed it gains depends on two things: how fast it throws that mass, and how much of the rocket's starting weight was the mass it threw. Tsiolkovsky's equation says that the velocity change you achieve equals your exhaust velocity multiplied by the natural logarithm of the ratio between your starting mass and your final mass. The logarithm is the problem. Logarithms are gentle, and their inverses are not. Turn the equation around and ask, how much mass do I need to start with in order to reach a given speed? And the answer grows exponentially with the ratio of your target speed to your exhaust velocity. Not linearly, not as a square, exponentially. Let me show you what that does with real numbers, and let me do it for a target of 10% of the speed of light, 30,000 kilometers per second, because that would put Proxima Centauri about 42.5 years away one way, which is at least a span a person could conceivably live through. Start with chemical propulsion, which is what every rocket ever launched has used. The best chemical engines achieve an exhaust velocity of about 4.4 kilometers per second. To reach 30,000 kilometers per second, the ratio of target speed to exhaust speed is about 6,800. Raise the mathematical constant E to that power, and you get a required mass ratio of roughly 10 to the power of 2,960. I want to be precise about how large that number is, because I do not think the exponent communicates anything on its own. 10 to the power of 2,960 means one followed by nearly 3,000 zeros. For comparison, the total number of atoms in the entire observable universe is somewhere around 10 to the 80th, a one followed by 80 zeros. So a chemical rocket that reaches 10% of light speed would need to start with more fuel than there is matter in the universe, by a margin of nearly 3,000 orders of magnitude. And you would then have to do it again to slow down. It is worth pausing on how unusual that is as a conclusion. Most engineering limits are practical. This one is not practical. There is no amount of money, no manufacturing advance, no clever staging, no material science breakthrough that closes a gap of 10 to the 2,960th. Chemical propulsion is not merely a bad way to reach the stars. It is not a way to reach the stars. Move up the ladder, nuclear thermal propulsion, where a reactor heats hydrogen and blows it out a nozzle, actually built and test-fired in the 1960s under the NERVA program, gets you an exhaust velocity of about 9 kilometers per second, twice as good. The required mass ratio drops to about 10 to the power of 1,448, half the exponent, still catastrophically, unreachably impossible. Ion propulsion, which is real and flying today on missions like Dawn and Bepi Colombo, achieves exhaust velocities around 30 kilometers per second by accelerating charged particles electrically, 7 times better than chemical. Mass ratio, about 10 to the power of 434. Notice what is happening. Each genuinely enormous improvement in engine technology, a doubling, then a 7-fold gain, knocks the exponent down, but does not change the character of the answer. You're still asking for more mass than the universe contains. You're just asking for less absurdly more. Now go to fusion, which does not exist as a working drive but is at least physically legitimate, and assume a plausible exhaust velocity of 10,000 kilometers per second. Suddenly the ratio of target speed to exhaust speed is 3, and to the third power is about 20. That is 20 to 1. That is a real number. That is an engineering problem rather than an impossibility. A ship where 95% of the launch mass is fuel is roughly what a Saturn V was. The exponent has stopped being the enemy, and at the theoretical extreme, a perfect photon rocket that throws light itself backwards at the speed of light needs a mass ratio of about 1.1 to 1, which is to say, almost no fuel at all, relatively speaking. Which is the reason the entire field of interstellar propulsion is fundamentally a search for exhaust velocity, and always has been. So the picture looks almost hopeful. Get fusion working, get your exhaust up to 10,000 kilometers a second, and the equation stops eating you. Before we go further, there is a second way to look at the same wall that avoids the equation entirely, and I find it clarifying because it strips out all the engineering and leaves only physics. Forget rockets. Ask only how much kinetic energy a ship must be given, regardless of how you give it. A vehicle of 1,000 tons, about the mass of a large ferry, and not unreasonable for something carrying people and supplies, moving at 10% of the speed of light carries about 4.5 times 10 to the 20th joules of kinetic energy. Total world primary energy consumption, across every power station, every engine, every furnace, every fire on Earth, runs at roughly 6.2 times 10 to the 20th joules per year. So the kinetic energy of that one ship is about 9 months of everything human civilization uses. Not 9 months of the space budget. 9 months of civilization, converted with perfect efficiency into motion in one direction, which is not a thing that any process does. Include the deceleration at the far end, and you're at about a year and 5 months of total human energy output. Push the speed to 20% of light and the energy quadruples, because kinetic energy goes as the square of velocity. Now you are at about 3 years of global energy one way, nearly 6 with braking. Here is why I said this is clarifying. Those are enormous numbers, but they are not impossible numbers. They are bills. A civilization with 20 times our energy production could pay one without particular strain. Nothing in physics forbids it. Energy is the kind of obstacle that gets smaller as a species gets richer. Remember that, because it is going to matter at the end of tonight. The energy wall is real, and it is the one people always name, and it is not the wall that stops this. Except we have been ignoring something, and it is the single most consistently overlooked fact in popular discussions of interstellar travel. You have to stop. Every number I just gave you is for acceleration only, for getting up to 10% of light speed. A ship that does that and nothing else arrives at Alpha Centauri travelling at 30,000 kilometers per second and crosses the entire system, from outer edge to outer edge, in a matter of hours. It photographs whatever it can on the way past, and then it keeps going, forever, into empty space, and it never comes back and it never returns. If you want to actually arrive, to slow down, enter orbit, look at things for longer than an afternoon, you need the same velocity change again in the opposite direction. And because the mass ratio is exponential in velocity change, doubling the velocity change does not double the mass ratio, it squares it. Fusion's tidy 20 to 1 becomes about 400 to 1. Ion's absurd 10 to the 434th becomes 10 to the 868th. Chemical's already impossible 10 to the 2960th becomes 10 to the 5920th. And that squaring is why nearly every serious interstellar mission study you will ever read is a flyby study. Not because flybys are interesting, because braking is a second, equally large problem stacked on top of the first, and the moment you add it, designs that were merely extraordinary become designs that are not designs at all. There is one escape route from the equation, and it is worth naming because it is the basis of the most famous modern proposal. If the mass ratio is the problem, do not carry fuel, leave it at home, build the energy source on Earth, a laser array say, and push the vehicle from behind with light. The ship carries no propellant, so there is no exponent, and the achievable velocity is limited only by how long you can keep the beam on target and how much acceleration the structure survives. That is a genuinely clever answer, and it works, and it comes with a cost that is going to matter enormously in a few minutes. A ship pushed by a laser from Earth cannot slow down. There is nobody at Alpha Centauri to build the second laser, so the equation has left us in a very specific place. Every method that can carry a useful payload cannot reach a useful speed. Every method that can reach a useful speed cannot carry a useful payload. And the one method that escapes the equation entirely arrives at the destination unable to stop. That raises the question of what people have actually proposed in detail on paper, with numbers, because serious, capable, unromantic engineers have been attacking this problem for nearly 70 years, and what they came up with is more impressive and more sobering than most people realize. I want to walk up the ladder of real proposals in order, and I want you to watch what each one gives up in order to buy its speed. That pattern, what gets sacrificed, is the whole lesson of this section. The first rung is Project Orion, studied in the United States from 1958 to 1963 by a team that included Freeman Dyson and Ted Taylor. The concept is so blunt it sounds like a joke until you look at the numbers. You build a very large ship with a thick steel plate on the back, mounted on enormous shock absorbers. Then you drop nuclear devices out of a chute behind it and detonate them, one every second or so, and ride the shock waves. It is grotesque, and it works. The physics is sound and was verified with chemical explosive test models. Orion was the only interstellar-capable propulsion concept ever taken seriously by a government, and it was killed not by physics, but by the 1963 Partial Test Ban Treaty, which prohibited nuclear detonations in space. In 1968, Dyson published a paper called Interstellar Transport that worked out what Orion could actually do if you pushed it to its limits. The version he called Energy Limited reached roughly 3.3% of the speed of light, which puts Alpha Centauri about 130 years away. And Dyson, having done that arithmetic, wrote down the observation that I think is the most important sentence anyone has produced on this subject. He noted that a voyage of that duration is not a project for a person, it is a project for a society. Sit with that for a moment, because of who said it and when. This is one of the sharpest minds of the 20th century, at the exact moment that interstellar flight became technically describable for the first time in history. Not fantasy, not speculation, but a design with a mass budget and a delta V figure. And the very first thing he identified was not an engineering problem. It was that the ship would have to be handed to strangers. Nobody who authorized the launch would see it arrive. Nobody who built it would. Nobody who was alive on the day it left would still be alive when it got there. The instant interstellar travel became real enough to draw, it stopped being something a human being could personally do, and became something a civilization would have to do on behalf of people it would never meet. The second rung is Project Daedalus, developed by the British Interplanetary Society between 1973 and 1978, and it remains the most detailed interstellar starship design ever produced. A team of volunteer engineers and scientists spent 5 years working it out properly, and the result is a document that still repays reading. Daedalus was a 2-stage fusion rocket, igniting pellets of deuterium and helium-3 with electron beams at a rate of 250 detonations per second. Total launch mass, 54,000 tons. Fuel, 50,000 tons of it, the helium-3 to be mined from Jupiter's atmosphere over a 20-year campaign by floating extraction plants. Payload, 500 tons of instruments. Cruise velocity, about 12% of the speed of light. Target Barnard's star at just under 6 light-years, chosen over Alpha Centauri because at the time it was thought to have planets. Mission duration, about 50 years. And what did Daedalus give up? Everything at the far end. It had no brakes, none. The design has no deceleration stage at all, because adding one would have squared the mass ratio and made an already titanic vehicle impossible. Daedalus would have crossed Barnard's star's system at 36,000 kilometers per second, taking data for a matter of hours after a 50-year cruise, and then continued out into the galaxy forever. That is 50 years of flight for an afternoon of observations. The third rung is Project Longshot, a 1987 study by NASA and the United States Naval Academy, and it is the one design on this list that took arriving seriously. Longshot was to be assembled in orbit, powered by a fission reactor, driven by fusion pulses, and, crucially, it carried a deceleration stage. It would slow down and enter orbit around Alpha Centauri b. It achieved about 4.5% of light speed and a transit time of roughly 100 years. And what did Longshot give up? Speed and realism. Adding the brakes cost it 2/3 of Daedalus's velocity and doubled the mission duration, and the resulting vehicle mass made it a paper exercise from the start. It is a serious, careful design for a ship nobody was ever going to build. The fourth rung is the modern one, and it is where the ladder changes shape completely. Breakthrough Starshot was announced in April 2016 with a $100 million pledge, backed by Yuri Milner and endorsed on stage by Stephen Hawking and Mark Zuckerberg. The idea abandons the rocket equation entirely. You build a laser array on the ground with a power of roughly 100 gigawatts, comparable to the entire electrical generating capacity of a mid-sized country, and you fire it, for about 10 minutes, at a sail 4 meters across and a few atoms thick, with a chip glued to it. The acceleration is around 40,000 times Earth gravity. The final velocity is about 20% of the speed of light, transit time to Alpha Centauri, roughly 21 years. And what did Starshot give up? Almost the entire concept of a spacecraft. No fuel, no engine, no brakes, and a payload measured in grams, a camera, a small processor, a laser for sending data home, and nothing else. It would cross the Alpha Centauri system at 60,000 kilometers per second, photographing what it could in a window of hours, and continue on forever. Let me put you on one of those sails because I think the experience is worth feeling. There is nothing ahead of you. That is the first thing. At 20% of light speed, the stars in front are shifted slightly toward the blue and crowded a little tighter together by aberration, and the stars behind are reddened and sparse, and that is the entire visual difference between the fastest object ever made and standing still. Nothing streaks past. There is no sense of motion at all, but you're not moving through nothing. The sun sits inside a wisp of warm gas called the local interstellar cloud, about 30 light-years across, with a density of roughly 300,000 hydrogen atoms per cubic meter. That is a better vacuum than any laboratory on Earth has ever produced, and at your speed, every one of those atoms arrives with the kinetic energy of a particle from radioactive decay, millions of electron volts each, a continuous forward sleet of radiation that nothing in terrestrial engineering has ever been designed against, hour after hour, for 21 years. And somewhere in those 21 years, statistically, a grain of dust finds you. 1/10 of a milligram, invisible on a fingertip, arriving at 60,000 kilometers per second. It carries about 45 million joules, the energy of roughly 11 kilograms of high explosive. You are 4 meters of film weighing a few grams. There is no shield. There was never a shield. The proposed solution was simply to launch thousands of sails and accept that most of them would not arrive, which is an honest answer, and also tells you exactly what kind of journey this is. There are 2 more concepts worth naming, because they come up constantly, and both of them fail in instructive ways. The Bussard interstellar ramjet, proposed by Robert Bussard in 1960, is the most elegant idea anyone has ever had about this problem. If the trouble is carrying fuel, then scoop it up along the way. Interstellar space contains hydrogen. Deploy an enormous magnetic funnel. Gather that hydrogen as you go, fuse it, and throw it out the back. A ramjet never runs out and never has a mass ratio, because it is refueling continuously. It could in principle accelerate indefinitely. Robert Zubrin and Dana Andrews took the concept apart in the 1980s, and the answer is brutal in its simplicity. The magnetic scoop required to gather that thin hydrogen produces drag against the interstellar medium, and the drag exceeds the thrust the fusion can generate. A Bussard ramjet does not accelerate. It decelerates. The most beautiful idea in interstellar propulsion turns out, on close inspection, to be a very sophisticated parachute, which, to be fair, has led some people to suggest using one deliberately as a brake. Antimatter is the other perennial. It is the densest energy store physics permits. Complete annihilation releases about 9 times 10 to the 16th joules per kilogram, which means a fully efficient antimatter drive would need only a few kilograms for this entire mission. The obstacle is not theoretical. Global antimatter production, across every particle accelerator on Earth, is measured in nanograms per year, at an energy cost billions of times greater than what you get back, and there is no storage solution. Antimatter annihilates on contact with ordinary matter, so it must be held in magnetic traps in vacuum, indefinitely, without a single failure, for the entire duration of a decades-long flight. So look at what the ladder actually shows. Orion bought 130 years by giving up the notion that the crew and the builders are the same people. Daedalus bought 50 years by giving up the ability to stop. Longshot bought the ability to stop by giving up half its speed and any prospect of being built. Starshot bought 21 years by giving up the ship. Every rung purchases speed with something the mission needed. And Starshot's 21 years is the fastest number on the board, the best any human being has ever proposed, resting on physics that works, at a cost that a wealthy country could plausibly bear. That is 21 years, and then you still have to hear about it. Suppose it works. Suppose the array gets built and the sails get launched and one of them survives the dust and arrives, intact and functioning, at Alpha Centauri. Here is what you have actually purchased. Light takes 4 years and 3 months to travel between here and there. So does radio, and so does any laser signal, because they are all the same thing moving at the same speed. That means a question asked from Earth and answered from Alpha Centauri takes about 8.5 years to complete the round trip. For the bright pair, it is closer to 8.7. I want to convert that into human terms because 8.5 years is not an abstraction. It is a substantial fraction of a working life. If you send a question on the day you turn 30, the answer arrives after your 38th birthday. Children born on the day of transmission are in secondary school when the reply lands. Governments change twice. Most people change jobs at least once, often twice. Whatever was urgent about the question when you asked it has almost certainly stopped being urgent by the time it is answered. And the consequence of that latency is not that the mission is slow to operate. The consequence is that the mission cannot be operated at all. Everything we understand about running a spacecraft assumes a conversation. Mission control notices an anomaly, examines the telemetry, discusses options, uploads a fix. That loop is the fundamental unit of spaceflight operations, and it has saved missions repeatedly: Apollo 13, Hubble's mirror, Voyager 2's stuck scan platform, Kepler's failed reaction wheels. When something goes wrong, people on the ground work the problem and talk the machine through it. At interstellar range, that loop does not exist. A fault detected on arrival was already 4 years and 3 months old when its signal left. Any instruction you send in response arrives 4 years and 3 months after you send it, by which time the situation is more than 8 years removed from the moment you were reacting to. There is no troubleshooting. There is no course correction on advice. There is no talking the machine through anything. There is only the launch, and then the waiting, and then whatever happens happens on its own, and you hear about it years afterward as a piece of history. Let me put you in the room for that. It is the night the signal is due. The mission left 21 years ago, and the encounter, the actual arrival, the entire scientific return of the whole enterprise, took place 4 years and 3 months ago, and everybody in this room knows it. The probe crossed the Alpha Centauri system at 60,000 kilometers per second. It went from useful range to useless range in a matter of hours. It did whatever it did, correctly or not, and then it left the system on the far side and kept going, and it is now further from Alpha Centauri than the Earth is from the Sun by an enormous margin, and it will never stop. Everything that mattered is already over. It has been over for 4 years. The universe has simply not delivered the news yet. So the room waits. The receivers are pointed at a spot in the southern sky. Somebody has the acquisition time on a screen, calculated years in advance and adjusted for every correction anyone could think of. And the thing everybody is watching for is not an event. It is a delivery. A package posted before some of the people in this room had this job. The signal, if it comes, is a whisper. A gram-scale probe carries a laser measured in fractions of a watt, and the received power at this distance is a number with 30 zeros after the decimal point. The data will not be a photograph in any sense you would recognize. It will be bits, arriving slowly, over hours or days, and the image will be assembled afterward, and there will be arguments about whether some of it is noise. And whoever built that instrument is 25 years older than they were at launch. Some of them are not in the room, some of them are not anywhere. That is what arrival looks like at 4.24 light years. Not a landing, not a moment, a slow delivery of an old letter to people who have aged out of the question. There is a knock-on effect of that latency that I think is underappreciated, and it concerns not the machine but the people. A mission you cannot operate is a mission you cannot staff in the ordinary way. Every space agency on Earth runs on the assumption that a mission has a team, and the team has a job, and the job consists of doing things. Interstellar flight breaks that arrangement completely. Between launch and encounter, there is nothing for anyone to do except maintain a receiving capability and keep the pointing solution updated. For 2 decades, at minimum, with no data, no milestones, no images, no results, and no way to demonstrate to anybody holding a budget that the money is still being usefully spent. Consider what that does in practice. Voyager has been an operating mission for 49 years, and it has stayed funded because it kept producing results. Planetary encounters through the 80s, then heliosphere science, then the crossing of the heliopause. There was always something arriving. Take all of that away and leave only the waiting, and it becomes very difficult to describe what the team is for. This is not a criticism of anybody's seriousness. It is a structural observation about how long-duration projects survive, and it is going to matter enormously by the end of tonight. We have already had a small rehearsal of this, incidentally, and it is instructive. In 2020, the Breakthrough Listen project was combing through radio observations of Proxima Centauri and found something, a narrow band signal at 982 MHz that appeared to drift in frequency the way a signal from a moving planet should, and that seemed to appear only when the telescope was pointed at Proxima. It was catalogued as BLC-1, Breakthrough Listen Candidate 1. It survived a year of analysis. For a while, a small number of people had genuine reason to wonder. It was terrestrial interference. The follow-up work traced it to equipment on Earth, and the signature that made it look like it was drifting with a planet turned out to be an artifact of the observing method. That is how these things almost always end, and the people who did the analysis did it properly and published the disappointment. But notice the shape of even that near miss. The nearest star is the single most observed target in the entire search for radio signals from other civilizations. It is the obvious first place to look, and the closest we have come is a signal from our own equipment. And the reverse direction is worse. We have transmitted deliberately only a handful of times. The Arecibo message of 1974, the most famous of them, was aimed at the globular cluster Messier 13, 25,000 light-years away, which makes its round-trip time 50,000 years. It was never a message. It was a demonstration of a capability, addressed to a place chosen because it had a lot of stars in it, with a reply time longer than the span since the last ice age. The best technical hope for actually moving data across this distance is optical rather than radio. Infrared lasers give enormously higher gain than radio dishes for the same power, because the beam can be made much tighter, and NASA has now flown a real demonstration of it, the Deep Space Optical Communications Package on the Psyche mission, which has returned high-rate data across tens of millions of kilometers. Tens of millions of kilometers. Alpha Centauri is 40 trillion. The demonstration has covered about 1/1,000,000th of 1% of the distance, and even optical communication runs into the same square law that governs everything else. Double the distance and you receive a quarter of the power. Alpha Centauri is roughly 1,000,000 times further than the Psyche demonstration, which means the received signal is about 1,000,000,000 times weaker for the same transmitter, a factor of 10 to the 12th. You can claw some of that back with a bigger aperture at both ends and a colder receiver and better error correction, and the people working on this are extremely good at clawing. But the gap is 12 orders of magnitude, and the transmitter is bolted to something that weighs less than a paperclip. The proposed workaround for Starshot was to use the sail itself as the transmitting optic, to turn the 4-meter light sail into a 4-meter lens and fire the data home through it. It is a genuinely clever idea. It also requires the sail to survive 21 years of dust and radiation, intact enough to still function as a precision optic, and to be aimed back at a target it has been receding from at 60,000 kilometers per second, and to know where Earth is going to be 4 years after the transmission leaves. So the communication picture completes the pattern we have been building all evening. The journey takes decades at best. The encounter lasts hours. The news takes another 4 years and 3 months to arrive, and nothing about any of it can be adjusted, supervised, or rescued from here. Everything I have described so far assumes there is a reason to go, that something is waiting at the far end worth 21 years of flight and 4 years of post. I have been putting off telling you what we actually know about that, and I have been putting it off deliberately because it is not encouraging. The history of planet claims in the Alpha Centauri system is, so far, mostly a history of retractions. I want to go through it honestly, because I think the pattern tells you something about the destination that no amount of propulsion engineering can fix. In October 2012, a team led by Xavier Dumusc published a paper in Nature announcing Alpha Centauri BB, a planet of roughly Earth's mass orbiting the smaller of the two bright stars every 3.2 days. It was found by the radial velocity method, watching the star's spectral lines wobble as an unseen companion tugged it back and forth, and the wobble in question was about 50 centimeters per second, half a meter per second from 4 1/3 light-years away. It was an extraordinary measurement at the absolute limit of what the instrument could do. For 3 years, it was the nearest exoplanet ever discovered. In 2015, Vinesh Rajpal, Suzanne A. Grain, and Stephen Roberts published a reanalysis. The signal, they showed, was not a planet. It was an artifact, a ghost produced by the interaction between the way the observations were spaced in time and the way the data had been processed to remove the star's own activity. Feed the same processing chain a set of pure noise sampled at the same times, and a 3.2-day planet appears out of nothing. There was no planet. There had never been a planet. In 2021, a group led by Kevin Wagner reported something different. A thermal infrared source in the habitable zone of Alpha Centauri A, detected using the NEAR experiment on the Very Large Telescope. They called it Candidate 1, and they were careful about it, listing an instrumental artifact among the plausible explanations in their own paper. It has not been confirmed, and then, in August 2025, a team including Charles Beichmann of the Jet Propulsion Laboratory and Caltech reported something considerably more substantial, a coronagraphic detection using the James Webb Space Telescope's mid-infrared instrument, of a candidate giant planet in the habitable zone of Alpha Centauri A, roughly the mass of Saturn, on an eccentric orbit that would carry it between about 1 and 2 astronomical units from the star. Beichmann had proposed back in 2017 that Webb's 6.5-metre mirror might be able to do exactly this, and it appeared that it had. Then came the complication, and it is a beautiful illustration of how hard this is. Follow-up observations in February and April of 2025 failed to find it again. The team ran simulations of millions of possible orbits consistent with the original detection, and asked how many of them would have hidden the planet from the follow-up attempts. The answer was about 52%. Just over half the dynamically stable orbits would have placed the object somewhere the follow-ups could not have seen it, behind the coronagraph's mask or too close to the star or on the far side. So the candidate is neither confirmed nor refuted. It is quite literally a coin flip, and resolving it will take further observing seasons and the patience to keep looking. That is the state of knowledge about the 2 sun-like stars closest to Earth. One announced planet that turned out to be a processing artifact, one infrared candidate the authors themselves flagged as possibly instrumental, and one Webb detection that is currently a 52% chance of having been in the wrong place. It is worth being clear about why this is so much harder than it sounds, because Alpha Centauri ought to be the easiest system in the sky to study, and is in fact one of the hardest. The difficulty is the brightness, the same brightness that blinds Gaia. To photograph a planet next to a star, you must suppress the star's light by a factor of somewhere between 1 million and 10 billion, depending on the wavelength, while preserving the planets. Coronagraphs do this by physically masking the star inside the instrument, and the mask has to be placed with extraordinary precision, and everything that scatters or diffracts around it becomes noise sitting exactly where you are trying to look. A star as bright as Alpha Centauri A produces so much light to suppress that the residual scatter swamps anything Earth-sized. The proximity that makes it our most reachable target is the same proximity that makes it nearly impossible to examine. The second difficulty is that we are looking at the system almost face-on to its binary orbit, and more importantly, we have no reason to expect any planet's orbit to be edge-on to us. Transits, the workhorse method that found the great majority of the roughly 6,000 known exoplanets, require the planet to pass directly between us and its star, and the geometric odds of that alignment for a planet in a habitable zone are on the order of 0.5%. For our nearest neighbour, the single most important system in the sky, we simply did not get lucky. Around Proxima, the picture is firmer, and it is limited in a way that I think most people do not appreciate. Proxima b was announced in August 2016 by the European Southern Observatory's Pale Red Dot campaign, using the HARPS spectrograph. It has a minimum mass of about 1.07 Earth masses, an orbital period of 11.186 days, a semi-major axis of about 0.0485 astronomical units, and it receives roughly 65% of the light Earth gets, which, around a star that cool, places it inside the conventionally defined habitable zone. Proxima d, announced in 2022, has a minimum mass of about a quarter of Earth's on a 5-day orbit. Proxima c remains contested. Now, the caveat that should be attached to every sentence written about Proxima b, and usually is not. Radial velocity gives you 2 things, an orbital period and a minimum mass. That is all. It does not give you a radius. Without a radius you have no density, and without a density you have no idea whether the object is rocky, or a small gas envelope, or a water world, or something with no analogue in our system. Proxima b has never been observed to transit its star from our line of sight, which means there is no transmission spectrum, which means there is no observational evidence about its atmosphere. There is no evidence that it has an atmosphere at all, and there are strong reasons to doubt it does. Proxima is a flare star, and an aggressive one. In May 2019 it produced a superflare that brightened it by roughly 14,000 times in the ultraviolet over about 7 seconds, reported by Meredith McGregor and colleagues in Nature Astronomy in 2021. 7 seconds. A planet orbiting at 1/20th of the Earth-Sun distance receives that at close range, repeatedly, across billions of years. Work by Ignacy Ribas and by Cecilia Garafo and colleagues, both in 2016, put the X-ray flux at the planet's orbit at something like 400 times what Earth receives, and the standard modelling says that kind of sustained irradiation strips an atmosphere from a small planet over geological time. On top of that, a planet that close to a red dwarf is almost certainly tidally locked, showing the same face to its star permanently. That gives you a day side under unending light, a night side frozen solid, and a narrow ring of twilight between them where any interesting chemistry would have to live. I want to be fair to the optimistic reading, because it exists and it is not silly. Red dwarfs like Proxima are by far the most common kind of star in the galaxy, something like 3/4 of all stars, and they burn so slowly that they remain stable for hundreds of billions of years, far longer than the current age of the universe. If life can establish itself around one, it has an amount of time to work with that dwarfs anything available around a star like our Sun. Flares are violent, but a planet with a strong magnetic field, or a thick enough atmosphere, or an ocean thick enough to shelter chemistry well below the surface might ride them out. Some modelling suggests a tidally locked world with an ocean, and an atmosphere could redistribute heat well enough to keep a broad temperate band rather than a narrow ring. All of those are possibilities, and every one of them is currently unfalsifiable, because we have no radius, no atmosphere, and no direct observation. That is the honest position. Not that Proxima b is dead, that we cannot say anything about it at all beyond how long its year is, and roughly how heavy it must be. So let us assemble the destination honestly. The nearest star is one that no human has ever seen. Around it is one confirmed planet, about which we know a period and a lower bound on mass and nothing else. No size, no density, no surface, no air, orbiting inside the reach of flares that brighten 14,000-fold in seconds. Around the two sun-like stars next door there is one retracted planet, one uncertain infrared source, and one Webb candidate that is currently a 52% proposition. And the geometry of the double star means that whatever is there is confined to the inner 2 or 3 astronomical units, because a second sun swinging past at 11 astronomical units clears out everything further. We have not decided to go to Alpha Centauri because there is something there. We have decided it is the place we would go if we went anywhere, because it is the nearest, and being nearest is the only qualification it has. So now we have the whole picture, and I want to put the 3 obstacles side by side, because 2 of them are the ones everybody names, and the third is the one that actually ends this. Ask almost anyone why we have not gone to the nearest star and you will get one of 2 answers. Either it is too far, or we do not have the technology. Both answers are correct and both answers are shallow, and I want to lay them out properly so that when the real answer arrives, you can see precisely where it does not fit either of them. The first wall is speed. Light itself takes 4 years and 3 months to make the crossing. That is not a limitation of our engineering. It is the structure of the universe. The speed of light is not a speed limit in the way a motorway has a speed limit. It is closer to a property of geometry, the conversion factor between space and time, the rate at which cause reaches effect. Nothing carrying mass reaches it, and approaching it costs energy that climbs without bound. Get a ship to 86% of light speed and its effective mass has doubled. At 99.9% you are pushing something that behaves as though it weighs 22 times what it did at rest, and every further increment costs more than the last forever. That is a genuine wall, and it is absolute. But notice what it actually says. It says the trip cannot take less than 4 years and 3 months. It does not say the trip cannot happen. 4 years and 3 months is a survivable interval. If speed were the only wall, we would already be planning. The second wall is energy, and we did this arithmetic earlier. A 1,000-ton ship at 10% of light speed needs about 4.5 times 10 to the 20th joules, around 9 months of the total energy consumption of human civilization, one way at perfect efficiency, with the deceleration doubling it. Push to 20%, and it is closer to 3 years, one way, 6 with braking. Those numbers deserve respect. They are not small, but they are unmistakably the kind of number that shrinks as a civilization grows. Global energy use has increased by roughly a factor of 25 since 1800. A society drawing even a modest fraction of the total sunlight falling on its own planet, and the Earth intercepts something like 10,000 times humanity's current consumption, could pay this bill without noticing it particularly. The energy wall is a bill. Bills get paid by people who become richer, so take both of those seriously and then set them aside, because if speed and energy were the whole story, the correct conclusion would be optimism. A wealthy, patient, technologically mature civilization clears both. There is no physics forbidding it. Every serious analyst who has looked at this in the last 60 years agrees that a sufficiently advanced society could, in principle, send something to Alpha Centauri and have it arrive, and yet nothing has ever left. Not from here, and, as far as anyone has ever detected, not from anywhere. Before I name the third wall, let me clear away the two remaining escape routes, because somebody's always about to raise them, and they deserve straight answers rather than dismissal. The first is the warp drive. In 1994, Miguel Alcubierre published a genuine solution to Einstein's field equations describing a region of space-time that contracts in front of a vehicle and expands behind it, carrying the vehicle along inside a bubble, while the vehicle itself never moves faster than light locally. It is real general relativity correctly derived. The problem is what it requires: a shell of matter with negative energy density, in quantities that appear to be forbidden by the quantum inequalities governing how much negative energy can be concentrated in one place for how long. Later work has been encouraging in a narrow sense. Bobrick and Martier in 2021, and Fuchs and collaborators in 2024, produced warp geometries that need only positive energy, but every one of those is strictly subliminal. They describe an exotic way of moving slower than light, which we can already do. The second is the wormhole. Solutions have existed since Einstein and Rosen in 1935, and Morris and Thorne showed in 1988 what a traversable one would require. The answer again is exotic matter, threading the throat, holding it open against its own tendency to collapse faster than anything could cross it. None has ever been observed. There is also no known mechanism by which one would come into existence with both ends somewhere useful. I am not raising these to be dismissive. They are legitimate physics being done by serious people. I am raising them because even if one of them worked tomorrow, it would not touch the wall I am about to describe, and that, more than anything else, is how you know the wall is real. There is a third wall, and it is not made of physics. Let me approach it sideways, through a piece of mathematics that I think is the most quietly devastating idea in the whole field. In 2006, Andrew Kennedy published a paper in the Journal of the British Interplanetary Society, formalising something he called the weight calculation. The premise is simple and hard to argue with. The maximum speed our species can achieve has been growing, not steadily, but persistently, and if you fit a curve to the last few centuries of it, you get something on the order of 1.5% a year. Now suppose you launch a ship today aimed at Alpha Centauri on a 400-year trajectory. 200 years from now, if the trend has continued at all, somebody launches a faster ship. That ship overtakes yours in flight. It arrives first. Your 400 years of committed effort, your entire crew and their descendants, are met on arrival by people who left 2 centuries after you did and got there sooner, and everything you were sent to discover has already been reported home. Kennedy worked out the optimal departure time for various destinations, and for many of them the mathematically correct answer is centuries from now. Leaving too early is not merely inefficient, it is a waste. That produces something genuinely nasty. The rational decision, at every moment, is to wait. And because the rational decision is always to wait, and the trend that justifies waiting continues only as long as somebody is developing the technology that nobody has a reason to build a mission around, the perfectly reasonable choice is to postpone, indefinitely, in every generation, forever. Nobody ever refuses to go. Everybody simply agrees that this is not quite the right decade. There is a variant of the same trap that is even harder to escape, and Kennedy noted it too. The moment you accept the logic of waiting, you also lose the reason to develop the technology that would make waiting worthwhile, because nobody funds a propulsion program for a mission that has been indefinitely postponed. The growth curve that justified the delay was itself produced by people building things for reasons that had nothing to do with going to Alpha Centauri, which means it is not a law of nature and it is not guaranteed to continue. The weight calculation quietly assumes that progress happens on its own, in the background, while everyone sensibly declines to act. That is a description of the third wall from the outside, but it is not the wall itself. It is a symptom. The wall itself has to do with duration, and specifically with what a duration is measured against. Every single number this evening has ended in a unit of time: 76,000 years for Voyager, 425 years at 1% of light speed, 130 years for Dyson's Orion, 100 years for Longshot, 21 years for Starshot, plus 4 years and 3 months of post. Every conversion, every propulsion system, every ladder rung resolves into a span, and we have been comparing those spans to the wrong thing. We have been comparing them to a human life, and asking whether a person could survive the trip, And for the faster designs, the answer is yes. A 21-year flight or a 100-year flight is within reach of a life or of a small number of them. That comparison makes the problem look tractable. But a human being does not launch a starship. A human being does not build a 100-gigawatt laser array or fund it for 2 decades before it produces anything, or maintain the receiving station for the 21 years the sail is in flight, or keep the pointing solution updated, or preserve the knowledge of what the data means so that when the signal finally arrives there is somebody left who can read it. Institutions do those things. Agencies, governments, universities, consortia, companies. And the honest question, the one nobody asks because it sounds like a question about paperwork rather than about physics, is not whether a person can survive the crossing. It is whether anything we have ever built can stay interested for that long. We have an answer to that question. We have had it for about a decade, and it is not a thought experiment or a projection or a model. It is something that happened, in public, recently, to the one interstellar mission our species ever seriously funded, and when you put that answer next to the arithmetic, the distance to Alpha Centauri stops being 4.37 light-years and starts being measured in a unit we have been circling all evening without ever quite saying out loud. At the very beginning of tonight, I flagged a phrase and asked you to remember it. People say that a journey like this takes lifetimes, and they say it the way you say a meeting lasted an eternity, as an exaggeration, a figure of speech, the thing you reach for when a number gets too large to feel. I want to take that phrase back now and use it properly, as a unit, and do the accounting in it, because it turns out to be the only unit that describes this distance honestly, and once you start counting in it, everything we have covered this evening rearranges itself into something much simpler and much worse. Here is the ladder again, converted. Voyager-class travel, chemical rockets and gravity assists, which is to say everything we have actually built and flown, takes about 76,000 years. At roughly 30 years to a generation, that is something like 2,500 generations. Our species, in anything resembling its current form, is around 300,000 years old. The journey is a quarter of the entire existence of humanity, handed down parent to child 2,500 times. 1% of the speed of light, the upper end of what most credible crude studies converge on, because anything faster makes the mass ratio unbearable. Takes 425 years. That is 14 generations. 14 sets of parents and children, none of whom chose to be aboard except the first, none of whom sees both ends, and 11 or 12 of whom live their entire lives in the middle of the journey, with no departure to remember and no arrival to anticipate. 425 years ago, the telescope had just been invented. Dyson's energy-limited Orion, at 3.3% of light speed, takes about 130 years. That is 4 generations, and it is the design Dyson himself looked at before writing that such a voyage is a project for a society, not for a person. Project Longshot, the only serious design that actually stops when it arrives, takes about 100 years. One very long life if you launched as an infant and lived to 100 and arrived having done nothing else. And Breakthrough Starshot, the fastest thing any human being has ever proposed, running on physics that works. 21 years of flight plus 4 years and 3 months for the first data to reach Earth. Add the roughly 2 decades of development the project itself estimated before anything could launch, and the whole enterprise runs about 45 years from the first funded meeting to the first image. A person who joins that program at 30 is 75 when the picture arrives. Look at what happens across that entire ladder. The number of lifetimes falls from 2,500 generations to 14 generations to 4 to 1, and then it stops. It does not go below 1. There is no rung, anywhere on the ladder of things human beings know how to build or have credibly designed, where the distance to Alpha Centauri costs less than an entire working life. That is the answer. Not kilometers, not years. Lifetimes. And the plural is doing all the work, because at no point does it become singular, and at almost every point it is many. And now the part that I think settles it, because it is not a projection, or a model, or a philosophical argument. It is something that happened. In April 2016, Breakthrough Starshot was announced with a $100 million pledge from Yuri Milner, with Stephen Hawking on the stage and Mark Zuckerberg on the board. It was going to be humanity's first interstellar mission. The physics was sound. The money was real. The people were serious. The public accounting suggests that under $10 million was ever actually spent, roughly $4.5 million of it, across about 30 research contracts for laser arrays and sail materials. Activity peaked around 2020 and 2021, and then, over the following 2 or 3 years, the funding thinned, the meetings stopped, and the communications quietly went away. There was no cancellation announcement. There was no failure. Nothing broke. The program simply stopped being something anyone was doing. The mission designed to cross the distance in 21 years did not survive 10 years of being an idea. That is the third wall, and now I can name it plainly. It is not speed, which only says the trip cannot be quick. It is not energy, which is a bill that a richer civilization pays without noticing. It is continuity, the ability of a group of human beings to want the same thing, fund the same thing, and remember why they wanted it, across a span longer than any of them will live. We are, as it turns out, spectacularly bad at that. For calibration, consider the closest thing we have to a success. Cologne Cathedral was begun in 1248 and completed in 1880. 632 years, and construction was halted entirely for more than 300 of them. The unfinished building standing with a medieval crane on top of it for centuries while everybody involved in starting it turned to dust. It got finished. It is one of the very few projects in human history to survive a multi-century handover intact. And it only survived because a religion carried it, not a government and not a company. It required no maintenance while it waited. It had no life support system to keep running, no pointing solution to update, no crew to feed. It just stood there, patiently, being a large unfinished stone object. Widen the survey, and the picture does not improve. The longest continuously operating human institutions are religious orders and a handful of universities, running to somewhere between 900 and 1500 years, and every one of them has changed its purpose several times along the way. The oldest continuously operating company anyone can document was Kongo Gumi of Osaka, a temple-building firm founded in the year 578, which lasted 14 centuries and then lost its independence in 2006 over ordinary debt. Governments rarely reach 200 years in a recognizable form. Corporations average a few decades, and there is a subtler failure underneath the institutional one, which is the decay of the knowledge itself. Voyager is 49 years old, and its operating team has turned over completely more than once. The engineers keeping it alive today are maintaining hardware designed by people who are dead, working from documentation written in a technical idiom that has to be translated, occasionally rediscovering how a subsystem works by experiment because the person who knew has been gone for 30 years. That is one mission, in one language, over half a century, with continuous funding and a functioning agency behind it. Now stretch it to 400 years. English from 4 centuries ago is difficult. English from 1,000 years ago is a foreign language requiring formal study. Whatever the mission was for would have to survive not just the institution, but the vocabulary it was described in. That is our best case. A 400-year voyage at 1% of light speed asks for the same continuity from an organization that must also keep several hundred people alive inside a sealed vessel every single day of it, without a single lapse, for 14 generations, with no way to ask anyone for help. So let me hand you back the number we started with. The number is 4.37 light years. Look at what is inside it now. It is not one distance. It is 2, 4.2465 and 4.365, depending which of 3 stars you mean, separated by 7,500 times the distance from the Earth to the Sun. It is not a fixed distance. It is shrinking by 700 million kilometers a year, and will start growing again in 25,000. It is not a distance measured by our best instrument, because our best instrument is blind to the 2 stars in question. It is a distance to a place most of humanity cannot see from where they live, containing a star that no human being has ever seen at all in 300,000 years of looking up. It is a distance you cannot aim at, because the target has moved and will keep moving. It is a distance that no scale model on Earth can contain, and at the far end of it is one confirmed planet whose size and composition and atmosphere are entirely unknown, and a handful of candidates, one of which is currently a 52% proposition, and underneath all of that, the thing itself, it is not a distance at all. It is a duration wearing a distance's clothes, and the duration is longer than the funding cycle, longer than the career, longer than the agency, longer in most cases than the language the mission was designed in. That is why the distance to Alpha Centauri is far worse than you think. Not because it is too far to cross, because everything about it is measured against the wrong thing, and when you measure it against the right thing, against how long human beings are able to hold on to a purpose, the crossing was never the hard part. There is nothing in physics forbidding this, nothing at all. A patient, wealthy, unified civilization could go tomorrow, in the engineering sense. The obstacle is not out there in the dark between the stars. The obstacle is that it takes lifetimes, and we have never once managed to give anything that many. Tonight, if you are somewhere south enough to have the sky for it, the pointers are up, 2 of the brightest stars you will ever see, showing the way to the Southern Cross. One of them is the nearest star system to the Sun, and the actual nearest star, the closest object in the universe outside our own family of worlds, is sitting 2 degrees away from it, too faint to have ever been seen by anyone. It has been there the whole time. It will be there tomorrow. It is coming slowly toward us at 22 kilometers a second, and it will be closer in 25,000 years than it has ever been, and it is entirely possible that nobody will be counting by then. Sleep well.